Welcome to another video on the iGetChem channel, where we help you learn chemistry the easy way by showing you how to do problems. This problem is similar to another one that we have just done, and I will make a link to that video at the end of this clip so you can refer to that solution. In that solution, we dealt with calculating the pH of a solution containing 0.0475 molar of HNO2. But in this problem, we're going to look at a solution containing that amount of HNO2, but in addition to that, it contains another weak acid in the mixture. So let me read the problem and then we'll get to the solution. Part A, calculate the pH of a solution containing 0.0475 molar HNO2 and 0.100 molar NH4Cl. Part B, calculate the concentrations of all dissolved species in this solution. Okay, let's take a look at the solution. As I've said previously, we looked at this problem that contains a solution of only HNO2, and the concentration of that was 0.0475 molar. But in this problem, in addition to this concentration of HNO2, the solution also contains another weak acid which comes from the ammonium ion in NH4Cl, and the concentration of that is 0.100 molar. So what we have in this case is a solution containing a mixture of two weak acids, and we want to calculate the pH of this solution. Now, for calculating equilibrium, if you have one equilibrium, all the concentrations must satisfy that equilibrium. But if you have two equilibria that are going on at the same time and they share some common species, then all of the concentrations have to simultaneously satisfy both equilibria. And you can imagine if you have a system with more than that, more than two equilibria, then it becomes even more complex. It turns out that even though the problem explicitly states that there are two weak acids in this mixture, there is actually another equilibrium that's going on in this mixture. So before I actually do the calculation, let me just write down all three equilibria so that we know what we are dealing with. So first of all, we have HNO2 acting as an acid, which then donates a proton to H2O, making it H3O plus, and itself becomes the NO2 minus ion. So you can look up the Ka value for that, and that turns out to be 4.0 times 10 to the minus 4. That's the first equilibrium, so let me just label that 1. The second equilibrium is, of course, the other one that we have to deal with, which is the dissociation of NH4 plus, which you get from dissolving ammonium chloride in solution. And so NH4 plus, acting as an acid, will donate a proton to H2O, making it H3O plus, and itself becoming dissolved ammonia, NH3. So you can look up the Ka value for that, and then it turns out that the Ka value for that is 5.6 times 10 to the minus 10. So that is the second equilibrium. So I mentioned that there are actually not only two, but a third equilibrium, and that third equilibrium is present anytime you have an aqueous solution, because the third equilibrium, which is always present, is the autoionization equilibrium of H2O. So that is H2O plus H2O going to H3O plus OH minus. And of course, the Kw of that is 10 to the minus 14. So that's the third equilibrium. So anytime you have a mixture of multiple equilibria, it becomes a very complex problem. And so we would almost always uh, uh, do problems that have one clear winner in terms of the acid strength of the mixture. So in this case, we have HNO2, which is a weak acid, but we also have NH4 plus, which is actually an even weaker acid. And then after that, we have H2O, which is an acid, but it's even weaker. And the way you can tell is by actually looking at the magnitude of these Ka values. So you see for HNO2, the Ka value is about 10 to the minus 4. But then when you go to the ammonium ion, it drops to 10 to the minus 10. And furthermore, H2O acting as an acid protonating itself has a equilibrium magnitude constant of a magnitude of 10 to the minus 14. So that's even weaker. So in this case, where we have three equilibria, but there is one obvious winner, we would use that winner that has the largest Ka value to pin down the pH, and after that, the other equilibria, because they are weaker, they will then conform to whichever that pH value is. So what we mean by that is, if you look at this problem, you will see that this first equilibrium, because it's large, will produce essentially all of the H3O plus in this mixture. And once that H3O plus is determined, then it will translate to the second equilibrium, which will then allow us to calculate the equilibrium concentrations of the NH4 plus and the NH3. And then that same H3O plus will then translate to the last equilibrium, which of course is going to tell us what the OH minus concentration is. So with that in mind, we can proceed to use the first equilibrium to calculate the H3O plus concentration. Now that is a problem that we have actually solved in the previous video. So again, I'll make a link at the end of this video to that solution so you can look at how that is done. Very briefly, you have HNO2 dissociating to give you H3O plus and NO2 minus with a Ka equals to 4.0 times 10 to the minus 4. You would have to set up an IC calculation for that. So let me write that down very quickly so you know what we need to do. And so in this case, the initial concentration of HNO2 is 0.0475. The concentration of H2O makes no difference because it's a pure liquid solvent, and the other two were 0 and 0 to begin with. So the change to reach equilibrium would be minus x, plus x, and plus x. And finally, the equilibrium value would be 0.0475 minus x, x, and x. And you will have to put these back into the Ka expression for HNO2. And then putting in the unknown values, you have 0.0475 minus x, and that Ka value is equal to 4.0 times 10 to the minus 4. And as we have shown in the last video, to solve that, you need to use the quadratic equation. And once you have done that, you will find that the value for x turns out to be equal to 0.00416. And you see that's a concentration for the H3O plus. That's also the concentration for NO2 minus. And now taking that value and subtracting that from 0.0475, then you can calculate the value for the HNO2 concentration. And that turns out to be equal to 0.0433. So those are all the concentrations associated with the first equilibrium, which is that one. And as we have said, because that equilibrium has the strongest Ka, it will dictate the pH for the solution. That is, that equilibrium alone will control the H3O plus concentration. And so we know that's given by this number. So once we have that concentration for the H3O plus, then we can plug that into the second equilibrium to try to calculate all the equilibrium concentrations. So let me set that up right here. So I'll try to fit it on the same page. NH4 plus H2O going to H3O plus NH3. So let's put down what we know about the initial concentrations. Okay, so for the H3O plus concentration, we have the answer from the first part of the problem, and we know that that is 0.00416. And for the NH4 plus concentration, the initial concentration is just going to be 0.100 because NH4Cl, when it dissolves in solution, will give you one NH4 plus and one Cl minus. So whichever the concentration is for the NH4Cl will also be the concentration for NH4 plus when it's dissolved. So that we know is 0.100. And so the initial condition for this is 0 before it goes to equilibrium. And now what we want to do is to calculate what those equilibrium values are. So in this case, you really don't have to follow through with the ICA calculation because the answer is actually pretty obvious. The reason is because the equilibrium value for this second reaction, namely this value, is quite small. So what we know is that the equilibrium lies far to the right. So if you have an initial mixture that has this amount of NH4 plus and this amount of H3O plus, whichever the concentration of NH3 plus at the end, that is this number right here, it's going to be a fairly small number. And what that means is that when the system comes to equilibrium, the value for both NH4 plus as well as H3O plus really have not changed that much. So this is roughly unchanged. And the H3O plus, as we have said, because it's controlled by the first equilibrium, is also roughly unchanged, 0.00416. So now essentially, out of the 3 equilibrium concentrations for this equilibrium, we know 2 already, except for NH3, so we can actually solve for NH3 concentration by putting everything back into the Ka for the second reaction. So Ka is equal to H3O plus NH times NH3 concentration divided by the NH4 plus concentration, and we know that is equal to 5.6 times 10 to the minus 10. And we can put in the values we know. The H3O plus concentration is 0.00416. The concentration for the NH4 plus is 0.100. And now the only unknown in this case is the NH3 concentration, which is right there. So let me scroll up a little to make more room. So continuing, you can see that 5.6 times 10 to the minus 10 is equal to 0.00416 multiplied by the NH3 concentration divided by 0.100. And so from that you can calculate the NH3 concentration from that equation. and this comes out to be 1.35 times 10 to the minus 10 molar. Okay, so that is the NH3 concentration. And we can also write down the NH4 plus concentration, and we know that is approximately just equal to 0.100 molar. Okay, so now we have everything except for the third equilibrium. We have one more ion in the solution, which is the OH minus. But of course, the OH minus concentration must satisfy this Kw equilibrium, and since we know the pH already, the OH minus concentration is fairly straightforward. So let me write this down. Kw 10 to the minus 14 is H3O plus and OH minus. So clearly the OH minus concentration is just Kw divided by H3O plus, which is 10 to the minus 14, divided by 0.00416. And that value turns out to be 2.40 times 10 to the minus 12. And so that's the OH minus concentration. Okay, I think we have everything except one last one, which is actually not involved in any acid-base equilibrium, and that is this one, the Cl minus concentration. Cl minus is also one of the dissolved species, but we have said that the dissolution of the ammonium chloride will give you exactly the same concentration of Cl minus equal to that one. So the Cl minus concentration should be equal to just 0.100 molar. Okay, so those are all the values for all the dissolved species in the solution. So just quickly recap, when you are dealing with the pH calculation of a mixture of several weak acids, you will pick the strongest one to use that to calculate the pH, because the strongest one, namely the one that has the largest Ka value, will drive the pH for the entire solution, and the other equilibria will then conform to that H3O plus calculation that you got from the strongest acid. Okay, so that's the solution for this problem, and we are going to do more problems on acid-base equilibria, so you can watch those videos when we post them. And remember, if you like this video and want more content from us on the subject, please do let us know by subscribing to the channel and liking this video. Thank you.